In this lecture, I am going to see if I can speed up a very common code construct, the class factory. Now, you might be wondering, what exactly is a class factory? Simply put, a class factory is a special class that constructs other classes on demand, based on some kind of external configuration data. You often see class factories being used when accessing databases. In code, we simply want to access the database, and we don't really care if the data happens to be stored in a Microsoft SQL Server database, an Oracle database, or a MySQL database. That is an implementation detail that the code should not have to worry about. So, in code, you might see something like this. In this example, the class connection factory is a class factory that knows how to create a database connection object for the sales data. So, if there is a setting somewhere in a configuration file that specifies that all sales data is stored in an Oracle database, then the class factory can use this information to return a system.data.oracleclient.oracleConnection class. You can see how class factories simplify the code enormously. You no longer have to worry about where certain data is stored. The class factory knows and will automatically return the correct connection object for each request. Class factories have another big advantage. They allow us to move data around at runtime. If at a certain point the sales data migrates to a MySQL database, all we need to do is to update the configuration file. On the next data request, the class factory will read the modified configuration data and return a MySQL connection object instead. To build a class factory, you need to complete this fragment of code. So the input is a string which contains the type of the class to be instantiated, and the desired output is an actual instance of that class. Now, this is actually a difficult problem to solve. The closest you can get at compile time is something like this. This performs really well because the compiler can compile any possible scenario we might encounter at runtime. But the disadvantage is that we have to anticipate every possible use of the class factory beforehand. For example, it's completely impossible to move the sales data to a MySQL database if we haven't anticipated the use of MySQL with a corresponding case statement beforehand. So this code is not very useful in a class factory, but it does have the best possible performance. I will add the code to my measurement later on to serve as a benchmark value. Okay, so a switch statement will not suffice. What else do we have? Another possibility is to use reflection. The system.reflection namespace has a very nice class called Activator that we can use to construct any kind of object we like, based on the name of its type. So I can rewrite the previous method to use reflection instead, and it will look something like this. Now, this is going to work perfectly in all scenarios. I can throw in any type name I like, and if the type exists, the Activator class will construct the corresponding class instance. It's perfect. However, this code has a big problem. Reflection is really slow. We will see how slow in a moment when I run the benchmark, but trust me when I say this is going to introduce a massive performance setback in your code. This does not always have to be a problem. We can assume that database connections are not going to be created all that often. Furthermore, opening a database connection is a much slower operation than constructing the class. So a slowdown in construction is barely going to be noticeable to the end user. Because of this, you often see the Activator class popping up in C# code. In non-critical code, there's absolutely nothing wrong with using a little reflection to suit your needs. But what about critical code, where top performance is crucial? Fortunately, there is another solution. I am going to show you a mind-blowing trick for constructing any kind of class at runtime with a performance that is comparable to the switch statement. Check this out. First, let's get back to the basic problem. We need to complete this method. This is a generic method that can construct any type. But a collection of specific methods would also be fine. So let's say I need to construct a class called myClassType1. Then I would need the following method. In common intermediate language, the body of the method is going to look like this. So here is the gist of the trick. I am going to dynamically create a delegate at runtime, write these two intermediate language instructions into it, and then call the delegate to create the class instance. Here's how it works. My class factory first receives the type name string, which describes the type of the class instance to create. The first thing the class factory does is check in a dictionary if the corresponding delegate has been created already. If so, the factory retrieves the delegate from the dictionary and calls it directly to create the class instance. If not, the factory creates a dynamic method and writes the new object and return instructions into it. It then wraps the method in a delegate and stores the delegate in the dictionary in case we need it again later. Finally, it calls the delegate to create the class instance. Creating a dynamic method delegate is really slow, even slower than calling the Activator class. But here is the thing. Once we have a delegate, we can keep calling it over and over again to create more class instances. And calling a delegate is much faster than using the Activator class. So there will only be a delay when creating the first object of a given type. Any subsequent call is going to be super fast. Okay, so let's take a look at my benchmarking program for this lecture. You can see in this constant declaration up here that I am going to instantiate 1 million objects. The first method, measure A, loops 1 million times and uses the static switch statement to construct the objects. You can see here that my program creates string builder instances and doesn't really support anything else. So the switch statement is a bit silly because it only supports a single class and cannot be modified in any way after compilation. But we'll keep it in here to serve as a benchmark value. It signifies the best possible performance when creating 1 million objects. Next up is measure B, which uses the Activator class to create the string builders. Really simple and clean code. And it's really a shame that it's not going to perform very well. You're going to see in a moment how slow reflection actually is. Finally, here is measure C. It uses a class factory called getClassCreator. This class factory returns a class creator, which you can see is actually a delegate for a method without any parameters that returns an object. The next line creates the string builder by simply calling the delegate. So all the magic happens in the class factory. The first thing the class factory does is try to retrieve the delegate from the dictionary. If the dictionary does not yet contain the delegate, the factory moves on and gets the constructor info for the string builder. It then creates a dynamic method and writes the new object and return instructions into the method. Finally, it wraps the method in a delegate and stores the delegate in the dictionary. Finally, down here, the main program method calls all three measure methods and displays the runtime in milliseconds. Okay, let's see how these three techniques measure up. I'm going to run the program. Check this out. And here are the results. The switch statement ran in 131 milliseconds. The Activator class took 11,377 milliseconds, and the dynamic method took 673 milliseconds. Here are the results in a graph. So the switch statement constructed 1 million string builders in 131 milliseconds. This corresponds to 7,633 objects created per millisecond. But the Activator class did much worse. It took a whopping 11,377 milliseconds to construct the string builders, which corresponds to only 87 objects per millisecond. The Activator class is 86 times slower than the switch statement. And finally, here are the dynamic method results. The dynamic method delegate constructed 1 million string builders in 673 milliseconds. This corresponds to 1485 objects per millisecond. So the dynamic method is 5 times slower than the switch statement, but it's almost 17 times faster than the Activator class. Okay, so what have we learned? A class factory is a class that constructs other class instances on demand using external configuration information. A common way to implement class factories is with the Activator class, but the Activator class is 86 times slower than static compiled code. A much better solution is to use dynamic method delegates. The dynamic method delegates are only 5 times slower than static compiled code and 17 times faster than the Activator class. In other words, if you replace the Activator class with dynamic method delegates in your class factory, you are going to speed up your code by a factor of 17.